Greetings to everyone. I am Aadittya Deouskar with my project Aorta, which is a computational framework with a linear regression model for precisifying aneurysmal therapeutics for reducing fatalities from abdominal aortic aneurysms. Coming on to my problem statement, which is abdominal aortic aneurysms or AAA. So basically, common cardiovascular disease with over 10 million cases per year in India and a high fatality rate of 40% pre-rupture to 90% post-rupture. In this, the abdominal aorta of the patient undergoes fast lateral expansion, due to which the arterial wall weakens and ruptures, resulting into internal hemorrhages, multiple organ failures, and ultimately deaths. Consulted local cardiothoracic surgeons are listed down the following flaws associated with the AAA therapeutics. The major flaw is the use of human estimations for the surgery planning, which is quite inaccurate and poses a direct threat to the patient's survivability. The cardiothoracic surgeons, on the basis of their clinical experience, decide the characteristics of the stent graft for EVAR surgery, which is crucial for the survivability of the patient. Human estimation is quite inaccurate because not all biological systems of every individual function the same. And since there are no current statistical methods for AAA therapeutics, this is a big flaw which causes direct fatality in AAA therapeutics. The basis of these flaws, in order to rectify these flaws, we propose a solution, the aorta guard. So basically, it is a therapeutical model with the primary objective of removal of inaccuracy. It is separated into two parts. First is the real-time 3D simulation, which uses computational fluid dynamics and finite element analysis on the basis of the geometrical data, which is directly acquired from the patient's CT scan, which makes it quite case specific. Then the other part is the a mathematical linear regression model, which is derived after surveying biomechanical factors affecting aneurysmal expansion. And using this MLR model, we are able to we are able to quantify the rate of expansion of the abdominal aortic aneurysms, and thus give a prediction about the rupture date of the abdominal aortic aneurysm. So coming on to the methodology, which is the rendering of a computational pipeline for case-specific CFD simulation for real-time flow analysis with the LR model. For the geometrical reconstruction of the abdominal aorta, I imported CT scans of the patient in .nrd format in an open source software called 3D Slicer, in which I performed threshold based depth segmentation and segmented out the abdominal cavity of the patient. And then using volume rendering RO, I was able to segment the abdominal aorta of the patient, in which I performed VMTK processing or vascular modeling toolkit, using which I was able to get the geometrical values like dimensions of the abdominal aorta, which will be later used as the variables for the regression model. This acquired geometry in STL format was imported into GMSH, in which I performed quadric edge collapse decimation. Then I exported this STL file in which I converted the STL to step file for easier mesh generation. Then this step file was imported into Ansys space claim, where I performed facet merging and then exported that file and imported into Ansys meshing editor, in which I used the sphere of influence method for reducing the mesh cell count, and also defined the inlets and outlets of blood flow using name selections. And using this, the mesh was generated. Imported this mesh into Ansys and used the K epsilon model for rendering the turbulent flow of blood simulation, and then defined the properties of the blood and extra other boundary inlet function, outlet functions, and everything. And using this, we were able to simulate the blood flow, which gave us the following three outcomes. First was the pressure contour on the arterial wall. Second was the velocity streamline of the blood at different sections of the abdominal aorta. And third was the eddy's viscosity in the volume of abdominal aorta. Moving on to the second section of the methodology, which is the derivation of a mathematical model, which uses biomechanical factors for calculating the growth in the abdominal aorta in T units of time. I surveyed available literature and research which formulated the biomechanical factors and biomechanical relationships between the aortic geometry and the expansion rate, and the factors that biomechanical factors that were contributing to the aneurysm are as follows: compliance, elastic modulus, and Poisson's ratio. And after modifying them for suiting into the arterial environment, these are the formulations that I got. After substituting these functions into a correlative function of the Laplace's law for arterial systems, I got this mathematical model, which basically utilizes the geometrical variables of the abdominal aorta and calculates the expanded size after t units of time. Using this mathematical model, I made a Python code, a very simple Python code that inputs the different variables, geometrical variables of the abdominal aorta acquired from the VMTK processing, and then uses the model and solves the model to give the expanded size of the abdominal aorta after the user defined time. So as of now, I have used 10 data sets for validation of the MLR model. Each data set comprises of a CT scan of the patient. And as you can see, these are the expansion rate results I got from my model. And right next to it are the uh, data expansion rate results that the researchers got after meticulous lab testing. And I got these CT scans from an online repositories like Aneurisk and NBI database. These are some metrics that I use for representing my model accuracy. Mean squared error, R squared, which is used for regression models, root mean squared deviation, and adjusted R square. So as you can see here, these values suggest that the model is satisfyingly accurate and can be used as a supportive tool in the AAA therapeutics, since there are no other statistical methods in existence. So summarizing the flow of quantification. So the abdominal CT scan is taken, and then geometric reconstruction is performed, and the simulation is rendered. Then we get values from the VMTK processing and the simulation solver, which are substituted into the Python code of the MLR model. And using these values, the expansion rate is quantified. And using the expansion rate, we estimate the rupture date to a certain extent, which will give an idea to the doctors when to perform the intervention, which will help the doctors in performing the surgery. The pressure contour of the arterial wall will help the doctors locate the highly pressurized zones of the abdominal aortic wall, which will drastically help in the planning of the stent graft surgery. Since even from a CT scan or MRI scan, you are not able to actually locate the pressure distribution across the arterial wall. And also it will reduce the number of imaging scans required by providing real-time analysis and predictions relating to the aortic geometry. So coming on to the conclusion, first is the reduction in fatalities from treatment planning as well as the surgical intervention by removing human estimation and using statistical and mathematical operations. And it will also reduce the cost of the treatment by reducing the number of imaging scans, and also accuracy in monitoring, because it will give real-time predictions instead of CT scan which occur periodically in a span of 2 to 3 months. Use machine learning techniques like k-fold cross validation and all to work on all those data sets to present more accurate metrics relating to the accuracy of the model, and also incorporate in clinical practice, and also enhancing the rendering simulation pipeline using RANS models like the Reynolds average, Navier-Stokes instead of the K epsilon to simulate the blood flow more accurately, and also creating an extension for 3D slicer which automatically segments out the abdominal aorta from the CT scan. So in order to save time for commercial use. So these are the following references that I used for my development of my model and literature analysis. And also I consulted multiple cardiothoracic surgeons in order to gain their feedback on the actual efficacy of the model, like how actually it is useful for them. And also I consulted mathematical professors from NIT and foreign colleges to validate the mathematical correctness of this project. And I have this is it. This is my project. Thank you.